3 plus 2 5, 4 plus 4 8. Similarly 5 plus 3 8, 2 plus 1 3, 1 plus 2 3. And if we transpose it, then we get 3 8 5 3. Then the rows gets transposed to the into columns, and the first row is 3 8, second row 5 3, 8 third row 8 3. And if we take out the transpose of A and B separately, then originally A was 2 3 4 and 5 2 1, and the transpose become the row gets converted into column and the column gets converted into the row. So the first row becomes 2 5, second row becomes 3 2, and the third row consists of 4 1. And in case of B, the first row becomes 1 3, the second row becomes 2 1, and the third row becomes 4 2. So if we add this, we get 3 8 in the first row, 5 and 3 in the second row, and 8 and 3 in the third row. So which is equal to this. So we can say that A plus B transpose equal to A transpose plus B transpose. And if we come to this, then for example, if we take an matrix A with 2 by 2 matrix with consisting of element 2 5 3 1, and another matrix 2 by 2 matrix consisting of element 3 1 4 5, then on multiplication we get 2 into 3 6, and 5 plus 5 into 4 20, and second for the second element of the first row, 2 into 2, that is 2, and 5 into 5, that is 25. So similarly we will get the element of the second row, and if we add all the sum, and if we add up, then the final resultant will be 26 27 13 and 18. Now if we transpose it, the first row will consist of 26 and 13, and the second row will consist of 27 and 8. Now if we transpose A and B separately, we get 2 3 in the first row, 5 1 in the second row, and 3 4 in the first row, 1 5 in the second row. Now if we multiply this, we get 2 6 1 3 in the first row and 2 7 8 in the second row. So we can which is same as this one, that is AB transpose. So we can conclude that AB transpose is equal to B transpose into A transpose. Now we can talk about symmetric matrix. Now a matrix A is said to be a symmetric matrix if A is equal to A transpose, or we can say that the opposite elements are equal. What do I mean by opposite element is, suppose an element of the matrix is A1 2, this will be equal to A2 1. Suppose in A, the A matrix is this one, and if we transpose it, it becomes this. Both are same. So if we look at, so A is a transpose matrix. So if we look, sorry, I'm not transpose matrix, symmetric matrix. So if we look, then this is A21 is equal to A12, A31 is equal to A13, and A32 is equal to A23, and this can never be same because it is A11 and A22, A33. Only one element exists as with this value of ij. Ij means, I wanted to say this, Aij, possible values of ij. Only one is possible, that is 2 for diagonal elements, that is 2 2 1 1 3 3 4 4 depending upon the order. so this cannot be same with any other elements. Then skew symmetric matrix. For a skew symmetric matrix, a matrix has to be a square matrix. Then if a matrix Aij is said to be a skew symmetric if A transpose is equal to minus A, means if Aj means it is the transpose, so the column, the row has become column and the column has become row, so we can write Ij as Aij as Aj, and that is equal to minus Ij for all possible values of I and j. Now if I equal to j, that is for diagonal elements, then we get Ai equal to minus Aii, that implies 2Aii is equal to 0, that implies Aii equal to 0. The diagonal elements of the skew symmetric matrix are always 0, as we have seen, as we have proved here. Now it comes to a theorem, that is, for any square matrix A with real number elements, then if this means if any square matrix A consists of real number, then we can conclude that A plus A, not only real number, all elements, I would say, any type of element. Then the symmetric matrix is defined as A plus A transpose, and the skew symmetric matrix is defined as A minus A transpose. For example, as we can see, the original matrix A equal to 3, 2, 1, 4, and the transpose matrix is 3, 1, 2, 4. Then if we add it up, then we get 6, 3 in the first row, and in second row 3, 8, and which is a symmetric matrix, as we can see that A21 is equal to A12. And if we subtract the transpose from the original matrix, we get 3, 2, 1, we get 0, 1 in the first row and minus 1, 0 in the second row, and we can see A12 is equal to minus A21. So this is a skew symmetric matrix. Now if we add it up, if we multiply the symmetric matrix with half and the skew symmetric matrix is with half, and we add it, then we get the original matrix. This is the second theorem, that is, any square matrix can be expressed as a sum of symmetric matrix and a skew symmetric matrix. Before doing the sum, we have to multiply it by half. Remember this. And then we come to the next topic, that is elementary operations of an matrix. Now elementary operations are of 6 types, 3 because of rows, and 3 for rows and 3 for columns. Now there are total 3 types, and 1 for row and 1 for column, so 2 into 3, 6 types of operations. Now the first one is interchange of any 2 rows or any 2 columns. Now we can change the ith row and jth column of any matrix with this operation, and if we want to interchange the ith row and jth row, we can write ri, this sign, and rj, means ith row and jth row. R signifies as row, and if we want to interchange any 2 ith, this will be column. And then we can write ci, this sign, and cj. C signifies as column, For example, if you take the matrix A of 3 by 3 order, which consists of element 1 2 3 4 5 6 7 8 9, then if we apply this operations of changing first row and second row, then the first row comes to the then the second row becomes the first row and the first row becomes the second row. Like in this will be the resultant. Now multiplication of elements of any row or column by a non-zero elements or constant k, suppose k or any number, anything. For example, if we take the example of previous matrix of A, if we take the example of A, then we want to multiply the first column, that is this one, with half. So we can write this C1, one arrow sign, and half C1. So then the resultant, all the elements of the first column will get multiplied by half. So the 1 into half becomes half. If we multiply 4 by half, that is 4 by 2 becomes 2, and 7 into half 7 by 2, and there will be no change with the rest of the elements. For 3, the third elementary operation is addition of any row or column. Suppose we want to multiply, for example, in this matrix, not in this matrix, the previous example we are taking, the of A, and we want to multiply it by 2 and subtract it from the first row. We want to multiply all the elements of the second row with 2 and subtract it from the first row. Then we can write it as R1 equal to R1 minus 2R2. Then it becomes, we have multiplied the second row elements with 2, so 4 becomes 8, and 1 minus 8 equal to minus 7. 5 becomes 10, so 2 minus 10 equal to minus 8, and 6 becomes 12, so 3 minus 12 equal to minus 9, and there will be no other change in the other elements.